Thank you. So encoding FP in Java is easier than in Go. Any idea why? Because Go does not have a parametric polymorphism, and it's really the bare minimum. We shall see why. This is a slide that you can take a photo of it if you want to review the presentation afterward. I highly recommend that you follow all the links after. I will be maybe quite fast for some of the stuff I will present, so it's a good idea to also activate the presenter notes if you want more explanation. So I was already introduced. So the i4j is a nice tool that I wrote. It generates a lot of stuff, and in particular, it makes it very easy to use algebraic data type in Java. And as you know, algebraic data types are the bread and butter of functional programming. So how many of you are using Java in their day-to-day job? Okay, so my apologies. So this talk is kind of consolation for you. That way that you can still use functional programming in your day-to-day job and maybe introduce a bit of FP to your colleague and show that it's quite practical until you can finally switch to a better language like Eta or Haskell. So I'm not going to argue this thesis, but I'll just say that Java has the minimum for functional programming, but it's still missing quite a few bits. Yeah, quite a few. And we shall see how to remediate this lack of support for functional programming. For IO effect tracking, the solution is to avoid side effects and instead to use an IO type and all the primitive associated with it. There's one in the library functional Java. I recommend it. In fact, I will use the functional Java API for this slide. Like F2 is B function, but it's shorter, so it's easier for the slides. Yeah, parametricity, it's very, very important. You can recover parametricity in Java by just ignoring everything that breaks it. It's quite easy. Some types, we shall see the Scott encoding and Church encoding of some types. You can get extensibility with object algebra and solve the expression problem. We shall see that lazy evaluation is a very essential tool for making a lot of algorithms very easy to write, like textbook Haskell implementation, and not worry about stack safety. And finally, HKT or type constructor polymorphism. There is no really any solution that are type safe. So there is an encoding, there's multiple encoding, but the one I recommend is the easiest, is based on paper lightweight polymorphism. It verifies a witness of the type constructors as a type parameter. I will not really talk about it, but there is some links at the end. There is one missing from the previous list. Which one? So it's tail crawl optimization. I have no solution. So you still need to write while loops. So if you have any way to influence the Java roadmap, first you ask for tail crawl optimization, and then type constructor polymorphism. I would be happy. So what can break parametricity? all of this, in particular, you don't catch any non-deterministic exception in pure code. You let that in, you can do that in the IO monad, but not in pure code. And you don't use any of the methods of Java-long object, in particular on universally quantified type variables, because then it breaks parametricity. The point of a universally quantified type variable is that you don't know anything about it. And if you can call methods on it, then you lose this essential properties of parametricity, and you lose all the free theorems that are associated with parametricity. So we are now assuming parametricity, and we still want to, let's say, prove that our encodings are correct. There is an easy way to view types as a set. To view types as set, we must ignore bottom values. We ignore nulls, and it's correct. It's morally correct to do so. So let's do that. So two types are isomorphic if they have the same cardinality. So here is a quick recap of the cardinality of basic algebraic data types. In particular, function. As you can see, the number of implementation of a function of a particular signature can grow quite fast. B to the A, which means that you need a test to be sure that you have the correct implementation for a given signature. So that's a lot. If it's an integer, you are not going to write all the tests. So what about polymorphic function? Because there we didn't talk about it. It's not polymorphic function. So what are the cardinality of those one? Any idea what is the cardinality? What's the number of implementation of this interface? Yeah? One, yes. Can you prove it?
No.
No. We'll do that. Foo. Does someone has any idea of which very well-known algebraic data type this is the encoding of? No? Either? I heard it. Yeah, it's either. Even more complicated just for the fun. So how do you compute cardinality of polymorphic function? You use the Uneda lemma. It says that for any functor f, you have this equivalence. So if we take the identity function, then first you introduce unit. X is equivalent to unit to x. Then you introduce the ID functor on the right-hand side. And here you get the exact form of the Uneda lemma, which means that this is isomorphic to ID unit. And ID unit is, of course, unit. Unit has only one inhabitants. So this means that we have proved that the ID function has only one inhabitant. So what does it mean also that you don't need to write any test. There's only one possible implementation, excluding bottom values. We can apply that to this foo polymorphic function. And I won't do it, but you get back the a plus b. So effectively, it's either. So here is another way that you can compute cardinality of polymorphic types is to lay out all the cases until you have all the polymorphic values in one line. So here's the first line. For the left case, you have 2a. So that means that you can create 4 possible pairs from this 2a. But you also have a Boolean value. And the Boolean value can be used to change the behavior. So if it's true, I do that, and if it's false, I do that. And this means that you have, in fact, not just 4 possible implementation, but 16. For the right-hand side, you have only 1 possible implementation because you have only 1 A. So this is easy. You have only 1 possible implementation, and the Boolean does not change that. And then you compute the overall cardinality by just taking the product of all the cases. So here it's 16 by 1, 16 possible implementation. What we have done here is that we have applied a fundamental theorem of parametricity, is that all the polymorphic value in the output of a function must come from the input of the function. The function implementation cannot create out of the blue a polymorphic value. It has to take it from the input. And this is why we can apply this reasoning. So this was more an excuse to practice parametricity, because I believe it's very useful to be familiar with it. And now let's see the real name for foo. It's easier. And we have seen the match function, but here is an implementation of the 2 constructors. So one calls the left parameter, and the other calls the right parameter. Does that make sense? So you have either in about 10 lines, so no excuse to don't use some types. Even if you don't have the refugee, it's quite easy to introduce an either data type in your project. There is a variation that uses an internal visitor instead of 2 functions. So I name this internal visitor cases. There's 2 cases, left and right, and depending on the constructor, it calls the left or right method. Does that make sense? This is a visitor, internal visitor, in fact, the implementation of the constructor. What is nice about internal visitor style is that you can easily extend it. So here is the says that extend either with a new case. So you have either right, either left, or you can have both value with says. And for that, you just extend the either cases interface and add the new case. What is very nice with this encoding is that you can transform an either value into a this value just by using method reference. Why? Because functions are contravariant, and in fact, here, thesis is a functional interface. It has only one abstract method here. So that's why you can use method reference in this way. So this doesn't work if you make it a class. So if you make it a class, it's a bit more work. And what we have done is that we have also solved the expression problem along the way, at least for non-inductive data types. We will see how it can be transposed to inductive data type as well. So derive for J can be used to skip the boilerplate. You just write the match method, and it will generate an either's classes with a lot of stuff. It can also generate type class instance from functional Java. In fact, it's not derive for J per se, but an extension. You can write your own type classes derivation. It's only about 10 lines. So it has been done for JSON codecs, for example. And it's compile time, type safe. It generates the constructors. You don't have to do it. It generates also pattern matching fluent syntax. It also generates a first-class pattern matching syntax as a function. And most importantly, the pattern matching syntax will ensure that you handle all the cases. If you don't handle all the cases, it will not compile. Another thing that is generated by DR4G is modifiers. For every field of your data type, a modifier is generated and it's polymorphic, which means that you can use it to implement the functor for either, for example. So now let's switch to extensibility and how to solve the expression problem in Java. The expression problem is stated as this. You have an algebra with two operations, literal and addition, and you have some interpreters for this algebra. What you want is to add both new interpreters and new cases while still reusing all the interpreters before you add the new case, and without modification of the previous interpreters. So because they have been compiled already, they are in an external library, you cannot touch it, but you still want to reuse the, let's say, the Eval interpreter. You just want to handle the new case. So how to do that? If you were there in the workshop this morning, in this room, it was there was an allusion to object algebra. Here they are. So here's the algebra for this this expression problem statement. So there's literals, there's addition, and here's a small program that makes use of it. So now, imagine that instead of an explicit algebra parameter, you have a type class constraint. What do you get in Haskell or Scala? Any idea? It's a final tagless style encoding. So object algebra are just a final tagless final style for Java. What is nice with this style is that you can easily extend it. So here we extend the original algebra with the multiplication case, and we create a new program that makes use of this case. If you want, you can verify this, this program into a value. And as you can see, it's very similar to a church encoding. Here is the interpreters for the object algebra. The Eval interpreter, quite straightforward. So it's one compiled unit. You cannot touch it anymore, but you want to reuse it when you add the multiplication case, and you do that. You just extend the original algebra, you implement multiplication, and you are done. So it's quite easy. But there's a few issues with this approach. Namely, the programs are a bit monolithic. There are monolithic faults, and if you want to, for example, serialize it, you cannot really do that easily. For that, you need an initial algebra, but hopefully there is an isomorphism between the two. So, this is, I will present one way to get this isomorphism. Step one, we introduce F algebra. In fact, object algebra are F algebra, but a special case of F algebra. Here we break down the induction instead of using E as a return type of the visitor, we use another other type variable, and we create a functor from this for a data type functor for these cases. Because we still use internal visitor, we can use the same extensibility. So by the way, we can see that the original exp algebra is exp cases with 2E. It's the same interface. We can extend it. Same thing. And now, step 2, we take the fixed point of the functor. So that means we take the visitor for the functor, and we replace the type variable with the name of the type. So here is, you see, E become exp. So we apply the fixed point combinator to this kind of, it's a way to do fixed point in Java. And now, to finally solve the expression problem, we need a way to use values that have been created in the first compilation unit and use them in the new compilation unit. So you need a way to easily translate an exp value into an expmul value. So the way you do that is that you initialize a factory that just is a visitor that that is implementing using the constructors of expmul, and you pass it to the catamorphism generated for exp. Catamorphism, this speak to you. It's for list, for example. What is a catamorphism for list? It's fold right. We'll see a list example further. So this way you can retrieve a way to translate an exp value in expmul value. So this solves the expression problem for the initial encoding. Here you see that we need this bit. It's a lazy constructor. So it's a way to suspend a supplier of a data type into a data type itself, and that way we create a sunk or memorized value inside the type itself. We can do that because since we use the visitor, we hide the constructor, and we have different ways that we can implement this match method. And one of the ways is to memorize another value that is evaluated once we call the match method. So why we need that is because otherwise we don't have stack safety. If we have a very nested exp value, if we don't suspend the computation, then we blow the stack. Another nice use of the exp functor is to create an anamorphism, that's a way to generate x value. It's very nice to implement. Left it as an exercise. So yeah, lazy evaluation is very central to this style of functional programming, because otherwise you have to deal with stack safety, and stack safety means that you have to write while loops in Java or use trampoline, and it makes the code very bloaty. On the contrary, if you use a lazy constructor, then you can almost take the textbook implementation in Haskell and translate it in Java. So for example, if we take a lazy list implementation, it's missing the @data annotation because we'll use the R4J. Here we name the two fields of the non-empty list case, id and tail. And here is the way we can implement filter. So filter can be implemented using fold R, and it's quite straightforward. Same for append. Append is you take a list, you replace this list by the original nil constructor of the list you want to append to. So this is a really textbook implementation of all these methods. Here is bind using the lazy. So all of this is possible because we have the lazy constructor. Otherwise, either you have to reverse the list for doing map or bind, or you have to. And if you reverse the list, then it doesn't work for infinite data structure. So this is nice because you can work with infinite data structure and you get laziness for free, almost. So here's the method that is generated by the R4J, the catamorphism method. For list, it could be named fold right. So you see it wrap every recursive call inside the delay constructor, which is the lazy constructor for the target type of your catamorphism. This is what ensures the type safety. The stack safety. Another common example is Fibonacci sequence. For that, you need an infinite stream. I already mentioned it, but for methods that benefit from TCO, tail call optimization, you still need to write for loops. This is a bit unfortunate, but otherwise you can get, almost like this is a Haskell implementation, and you translate it very straightforwardly into Java. The zip with implementation and this sequence itself are implemented using fixed combinator. This allows to avoid referencing, because an issue with the Lambda syntax is that you cannot do any self-reference. So for that, either you wrap your Lambda into an object that allows to do this dot and get a reference to the Lambda, or you use a fixed combinator that does that for you. So here's a zip with implementation and the fixed combinator. So it's a function from A to A. It only works because we have the lazy constructor. Of course, otherwise it blows the stack. We have the same kind of combinator for function and for B function. This is how laziness is implemented in the R4J. So it's a thread-safe, trampoline, lazy chunk. So you can try to find some issue with it, but I think it's quite correct. So why the trampoline is that because if you implemented, let's say, a lazy list, and if you have a long chain of chunk that get filtered out, if you don't do trampolining, then you blow the stack, even with a naive laziness implementation. So back to object algebra. Another limitation is that because you don't have a type constructor polymorphism, you cannot parameterize your carrier type. the type variable e. So this means that you cannot implement monads. You cannot implement more type-safe DSL. So for that, you need JADT, or also you need to, you kind of lose the extensibility of object algebra, because then you don't use object algebra anymore. For the unsafe, you can still use object algebra if you use the unsafe HKT encoding. I will refer you to these links to have an example of how to do that. But I will focus on JADT because it's safe. So what do you need for JADT in Java? It's the same as in Haskell 98. You need a witness of type equality. So a witness of type equality says that A and B are the same types. And why? Because there is only one implementation of this type, and this is this constructor that states that type equality is reflective. So A is equal to A. So this is the only instance of type A you have. So obviously it's safe. So how do you use it? Like this. So you pass it as a parameter to the visitor, and what it says is that the A type variable must be an integer. You don't know it, but here is a witness that tells you it is. So what it allows you is that you can write polymorphic evaluator for DSL. So you have a term of parameterized by t, and you can evaluate either to a Boolean or an integer. You cannot do that with object algebras. So here's the type X instance allows you to get back the equality between the type variable t and the concrete type Boolean or integer. So it's a bit more work, but it's worth it if you want to have richer DSL in Java. And also it's supported by derive4j that will generate all the constructor for you. So here's the one for literals. At construction time, it is known that the type variable is integer, so we can use the reflective constructor of type X to implement the constructor. Other nice usage of use of JADT is to implement single method services. So instead of having a bunch of methods in a service, you have only one, and you parameterize your commands with the type of the result you want. And that way you have only one method, and this gives you a lot more flexibility to compose it, because function compose much better than objects. So you can have a wrapper around this that provides transactionality or logging, stuff like that. You can also use JADT to implement almost free monads. This is an example in this project, Eval Interpreter. It's quite a bit of boilerplates, but here's a peek of how you would do that. You have this algebra. This is for event sourcing. Two operations that read from the event store, write to the event store, and this bind method that make it a monad. So this is the initial style encoding of monads that we have seen this morning, in fact. Further reading, so all of I have presented is documented in these links. So I highly recommend that you go through them. They are not very advanced, so it's quite accessible, I think. Yeah, that's all, folks. And remember, generic should be the tool of choice for abstracting over types. That's not me that say it, but Brian Gotts. So if you need an authoritative argument for commenting your colleague, it's this one. And as you have seen, I never used wildcards in this talk, and you don't need them. So now we will try these services. So we want to try it? Yes?
So when debugging that code using all that magic stuff, how ugly are the error message?
So the question is how more complicated all this encoding make debugging. So debugging with pure code is relatively easy. If you don't do side effects, usually what you get is compiled errors, and mostly the style where you don't debug at runtime, but you apply reasoning parametricity to your code to find what is the error. But in fact, it's not very complicated also to debug. You need just to add the breakpoint inside the visitor to see what is the value when only a particular case. So I never find any issue with it. Yeah. Any other question? I need 2 more. We can go back to some slides that you found not completely clear if you want. Yep. Okay.